Thanks for tuning into this revision zone video, part one of the energetics topic. In this video, we're just looking at some key concepts and basic definitions that are required to get a better understanding of this topic. So let's get straight to it. System and closed system is what we're going to look at first. Now, a system is quite simply just the reactants and products. So it's just the reactants and products, nothing else. Everything else, as we'll see later, is called the surroundings. So it's literally the chemicals of A going to B, where A is our reactants and B is our products. Nothing else can be your system. Now, a closed system is still our reactants and products, but so it's still our reactants and products, but we are not allowed to add or take anything away from this system. So I can't take products out, I can't put reactants in, and vice versa. This is the same principle throughout for closed systems. So I can either add or take away reactants in a system, but in a closed system I can't do that. And the same goes for products. Surroundings. Now, in regards to surroundings, really quite simple. Is anything but the actual reactants and products. So anything but the reactants and products. So this is where we start to include the beaker, so the container that the reaction is taking place in, the thermometer, the air, stirring rod, the table, anything but those reactants and products are classed as the surroundings. And it's really quite important. So for instance, e.g., the thermometer is part of the surroundings. It's not part of the system, and we'll look at that later on, why I'm emphasizing thermometer at this stage. Now, exothermic. Now, exo and endothermic reactions you will have come across at GCSE, and the definition remains the same. An exothermic reaction is a reaction which releases energy to the surroundings. On the system, so I could add that in here from the system. It's really quite important. So there's a couple of things we need to remember here. Thermic, thermal, so we're releasing energy, so normally in the form of thermal energy, but it releases energy. Exo, it exits the system, it is released. So we need to make sure we include that in our definition. Another few things that we need to remember about this definition and incorporate and do it while we're here is that the change in temperature for an exothermic reaction is always going to go up. So my thermometer will detect energy being released, and therefore the temperature will increase. A lot of students mix that up. They think, oh, energy is being released, the temperature from the system's losing energy, so the temperature will go down. That is not the case. And it's a common misconception that students have for some reason. But just remember, the thermometer is part of the surroundings. If you're not sure, that triangle there means delta, and that means change in, and that will pop up quite a bit within this topic, so please get used to or familiar with it. The other one is delta H. Now, you may have seen this at GCSE, and H is enthalpy, and we'll look at the definition of that in a moment. But that triangle means change again. It says the enthalpy change, and the enthalpy change here is negative. It goes down, and the units for that is kilojoules per mole, which I'll pop up here anyway, even though we're going to look at it later. Now, that means the enthalpy is the amount of energy within that system, and the amount of energy is decreasing, which means that that energy is being released from the system to the surroundings. So that's why we have it as negative. So if I could have minus 0.62 kilojoules per mole, I'm just making that up. Now, the other definition, the opposite of that, is an endothermic reaction. So it's a reaction, so RXN is just reaction if you're unsure, which absorbs energy from the surroundings. To the system, or into the system, you could write here, into the system. Okay. And we can look at the same two things that we did in the previous definition. Change in temperature, the system is gaining energy here, so it decreases. It will go down. The thermometer is part of the surroundings. It's realizing energy has been taken away from the surroundings and being absorbed into a system, and therefore we detect a temperature decrease. The enthalpy change will be positive because the amount of energy within the system is increasing. And again, that's kilojoules per mole. Always need to be putting signs in. So I could have plus 0.62 kilojoules per mole. So again, quite important here that we include signs always, always, always when it comes to thermodynamic calculations. Really, really important. The next definition we're going to look at is the enthalpy change. Now, the enthalpy change, as I've kind of discussed prior, is the amount of energy transferred between system and surroundings. But what I didn't include, it has to be a constant pressure and temperature. Normally we use standard states, sorry, not standard states, standard conditions, so 298 Kelvin and 100 kilopascals, or 1 atmosphere. So the enthalpy change here is the amount of energy transferred between system and surroundings. Between the system and surroundings at constant temperatures or pressures. Not all pressures, but and pressures. So these two things need to stay constant. Like I said, we normally use standard conditions, which we normally use this symbol to represent that. That's 298 Kelvin and 100 kilopascals. Those are standard conditions. It doesn't always have to be in standard conditions, so you may not see that, but they have to be constant. Right, so those are basic definitions that we need to learn. Make sure we are completely happy with them in order for us to be able to progress within this topic and get the fundamentals right, and not make those silly mistakes we don't need to make. Just remember here, like I've written above, that the enthalpy can be either positive for endo, or it can be negative for exo. But like I say, that finishes off the definitions. So let's have a look at a few concepts, and we're going to first have a look at these profile diagrams. This concept here, it's about illustrating the change in energy or the transfer of energy within a system. These energy profile diagrams, or sometimes called energy level diagrams, represent basically energy on the y-axis and some scale of time at the bottom. Sometimes we say displacement, we usually see that the x-axis is blank. Now, what we're going to do is we're just going to label this up. So this is my reactants. These are my products. So these blue lines underneath reactants and products represent the energy that the reactants have and the energy the products have. And we can see if we're starting over from the origin, if you like, that the overall energy has dropped, it has gone down. So if I draw an arrow in, just going down, okay, now that shows an overall decrease in energy. That drop is the enthalpy change, the change in enthalpy, and it's always negative. And remember, it's kilojoules per mole. Right now. And this is a very simple way of representing the change in energy within a system. But one thing it does illustrate is it illustrates that the enthalpy is negative. The system here is losing energy. Okay, so the change in energy will decrease, i.e. the enthalpy will be negative. Really quite important. Now, on the right-hand side, we've got a similar diagram, but this time we've made it look slightly different. We've inserted this almost peak within the diagram. Now, this gives us a little bit more detailed. It's not as limited as the one on the left. But if we look at the dashed lines, just continuing over the top and the bottom, we can see that the difference between them. Now, what I'm going to write here is actually R and P, just to represent reactants and products, and I'll do that going forward. That there's still a decrease. This distance here is exactly the same as the distance we just labeled before, and therefore that is the enthalpy, and it is still negative and kilojoules per mole. Now, but we have an addition to our diagram, and we have the difference between the reactant energy and the top of this peak. Now, again, you will have seen this at GCSE, but just in case you don't know, this is the activation energy. Normally, we write that as EA, but if we wanted to write that all out, it would be energy of activation. Okay, and it's always the difference in energy of reactants, and the top of that peak is the energy of activation, or activation energy. Just while we're here, we'll also label one other thing. The top of this peak is called a transition state. Okay, it's a transition state. It's a moment in which a reactant is transitioning into a product, if you like. It's not an intermediate. It is only a transition state. It's like a halfway house between reactants and products. So that is exothermic in terms of energy profile diagrams. Moving on to endothermic. Now, endothermic, again, I'm going to just label these lines as R and P, so reactants and products respectively. And we can see with endothermic that from reactants, starting from the origin, if you like, again, that this is going up. So that means this is increasing in energy. That means that the enthalpy, so the difference between the energy of reactants and products is always the enthalpy. So the change in enthalpy is positive here. And again, that's still kilojoules per mole, that SI unit for enthalpy. Very simple diagram, this energy level diagram, this energy profile diagram. It gives us limited information, but it's the information we want at this stage. We want to know that the enthalpy is positive. It explains that difference, that the energy of products is greater than the energy of reactants, whereas before, which I didn't mention, but whereas before with exothermic, the energy of reactants is greater than the energy of products. So I can write that here. Okay, so the energy of reactants is always greater than the energy of products for an exothermic reaction. Whereas an endothermic reaction, the reactants have a lower energy. The energy of reactants is always less than the products. So again, I'll just write energy here so we know what we're talking about. So that is a very simple energy level diagram. Moving on to the energy profile diagram with a little bit more information. Again, we've got this simple hill, if you like, there. And we can definitely see, if we look at these dashed lines, that there is an increase from reactants to products. And that is the same difference, essentially, as the one that I've done on the left. I'm just going to get rid of that additional line that we've got there. Now, the enthalpy, therefore, is all still shown as positive. So this type of diagram still shows that it's a positive enthalpy, but it also gives us an extra bit of information, and that is the energy of reaction. Now, a lot of students will tend to go from this line to, I wouldn't say a lot actually, a few students may think that it's this difference here. That is not the case, and I've seen it in questions where they put some arrows in, they label them and say which one's the activation energy. More of a GCSE question, but can happen at A-level. If I draw a straight line going from the energy of reactants to the top of that peak, that there is the activation energy, or energy of activation. It's always the difference from energy of reactants to the top of that peak. That is always the energy of activation. So that's the energy profile diagrams for endothermic. And it also concludes this video. It's a very short one to begin with. It's just these definitions that we must learn. But I hope it was useful. And if it was useful, please hit the like button and subscribe. And use the comment section to let us know what other videos you may want to see within chemistry. I hope you enjoyed that. We'll hopefully see you soon. Thank you.